October 19, 1942, Wright-Patterson Field, Dayton, Ohio. Major Thomas Thurlow stood in the secure briefing room of the Army Air Force's Materiel Command and examined the classified teletype that had arrived from Australia 3 hours earlier. The message was brief, but carried implications that would reverberate through American strategic planning for the remainder of the war. Japanese forces had recovered an intact Norden Mark 15 bombsight from a crashed B-17 flying fortress in the Solomon Islands. The device that represented America's most closely guarded bombing technology, the mechanical computer that had cost tens of millions of dollars and years of development, the optical precision instrument that supposedly made American strategic bombing feasible, from altitudes where enemy fighters and anti-aircraft fire had diminished effectiveness, was now in enemy hands. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed because tomorrow I've saved something extra special for you. The Norden Bombsight was not merely a piece of military equipment, it embodied an entire philosophy of strategic warfare, a belief system built on the conviction that precision bombing from high altitude could destroy an enemy's industrial capacity without the massive civilian casualties of area bombing. It represented American confidence in mechanical engineering, optical precision, and systematic methodology. Every bombardier in the Army Air Forces had sworn an oath never to allow the device to fall into enemy hands, yet here was confirmation that the unthinkable had occurred. What Major Thurlow and the intelligence officers at Wright-Patterson could not know in October 1942 was that Japanese technical intelligence had already begun a comprehensive examination of the captured device. Within weeks, Japanese engineers would complete an analysis that would fundamentally alter their understanding of American bombing doctrine. The conclusions they reached would prove both devastating to Japanese morale and grimly accurate in predicting the effectiveness of the strategic bombing campaign that would ultimately destroy Japan's capacity to wage war. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The story of the Norden Bombsight begins not with warfare, but with peacetime engineering ambition. Carl Lucas Norden, a Dutch immigrant engineer who had worked on gyroscopic stabilization systems for the United States Navy during the First World War, founded the Norden Laboratory Corporation in 1923. His goal was to develop a bombsight that could achieve unprecedented accuracy by compensating for aircraft motion, wind drift, and the complex ballistics of bombs falling through thousands of feet of atmosphere. The fundamental problem Norden sought to solve was straightforward to state but extraordinarily difficult to achieve. A bomb released from an aircraft at altitude does not fall straight down. It continues moving forward at the aircraft's speed while simultaneously falling due to gravity. Wind pushes it laterally. Air density affects its fall rate. The aircraft itself moves in 3 dimensions: pitching, rolling, and yawing. To hit a target from 25,000 feet, a bombardier needed to calculate the exact moment to release the bomb, accounting for all these variables simultaneously. Human calculation could not achieve this with any reliability. Existing bombsights in the 1920s were essentially graduated rings, mounted on telescopes, requiring the bombardier to estimate lead angles based on experience and judgment. Accuracy from 10,000 feet was measured in hundreds of yards. From 20,000 feet, bombs scattered across areas measured in square miles. Strategic precision bombing was simply not feasible with existing technology. Norden's insight was to automate the calculations using mechanical computation. His device would continuously measure the aircraft's ground speed and drift angle using optical tracking of the target. Gyroscopes would stabilize the sight platform regardless of aircraft motion. A mechanical computer would solve the ballistic equations in real time. At the precise moment when all variables aligned, the sight would automatically release the bombs. Development proceeded through the 1920s and into the 1930s, funded by United States Navy contracts. The Mark III version entered limited service in 1931. The Mark XI followed in 1933. Each iteration improved accuracy and reliability. By 1937, Norden had developed the Mark 15, the version that would become standard equipment in American heavy bombers throughout World War II. The Mark 15 bombsight consisted of approximately 2,000 individual parts, many machined to tolerances measured in 10,000ths of an inch. The stabilizer unit contained 3 gyroscopes, each spinning at thousands of revolutions per minute, mounted in gimbals that isolated the sight from aircraft motion. The optical system included multiple precision ground lenses. The mechanical computer used gear trains, cams, and differential mechanisms to perform continuous ballistic calculations. The entire assembly weighed about 50 pounds and required careful handling and regular maintenance by specially trained technicians. Operating the Norden required extensive training. Bombardiers attended months of instruction, learning not just how to use the device but understanding the principles behind its operation. They learned to calibrate the sight before missions, accounting for bomb weight, fusing, altitude, and expected atmospheric conditions. They practiced tracking targets through the bombsight telescope, keeping crosshairs aligned while the mechanical computer calculated release point. They learned emergency procedures for manual bombing if the device malfunctioned. The security surrounding the Norden was unprecedented. Each device carried a serial number. Storage facilities required armed guards. Before every mission, bombardiers signed custody receipts. Maintenance could only be performed by authorized technicians with security clearances. If an aircraft was damaged and forced to land in enemy territory, bombardiers were under strict orders to destroy the Norden using thermite grenades specifically provided for that purpose. The secrecy extended to manufacturing. Carl Norden's small factory in New York produced the stabilizer units. Bath and Stroud in England manufactured optical components under license. Final assembly occurred at secure facilities where workers were investigated and monitored. By 1942, American military doctrine had become inseparably linked to the Norden bombsight's capabilities. The Army Air Force's entire strategic bombing philosophy rested on the premise that precision attacks against specific industrial targets could destroy an enemy's war-making capacity. This stood in contrast to the Royal Air Force's area bombing campaign, which accepted that accurate targeting at night was impossible and therefore focused on destroying entire urban industrial complexes. American planners believed their approach was both more effective and more humane. Destroy the ball-bearing factories, the aircraft engine plants, the synthetic fuel refineries, and enemy production would collapse without the wholesale destruction of cities. The Norden bombsight made this vision theoretically achievable. Test range results supported American confidence. Under ideal conditions, skilled bombardiers using the Norden could place bombs within a circular error of 200 feet from 25,000 feet altitude. This represented accuracy improvements of several orders of magnitude compared to earlier bombsights. The United States invested enormous resources based on this capability. The B-17 Flying Fortress was designed around the concept of high-altitude precision bombing. Its defensive armament, pressurized crew stations, and turbocharged engines all served to enable bombing from altitudes where the Norden's accuracy could be fully exploited. Production of the Norden itself required substantial industrial capacity. By 1945, manufacturers had produced over 14,000 units at a total program cost exceeding $1.5 billion in then-year currency. When Japanese forces overran Allied positions in the Southwest Pacific during early 1942, they captured numerous American aircraft in various states of damage. At Clark Field in the Philippines, at Java airfields throughout the Dutch East Indies, and later at bases in New Guinea and the Solomon Islands, Japanese technical intelligence teams examined crashed or abandoned American bombers. Most of these aircraft had their Norden bombsights destroyed or removed before capture. Bombardiers had followed their orders, using thermite grenades to melt the precision mechanisms into slag or simply throwing the devices overboard before crash landing. But not all bombardiers succeeded in destroying their equipment. Some crashed with insufficient warning. Others were killed or incapacitated before they could carry out destruction procedures. A few aircraft made forced landings in areas quickly overrun by Japanese forces, giving crews no time to properly destroy classified equipment. By mid-1942, Japanese intelligence had recovered at least 2 relatively intact Norden bombsights, along with partial examples damaged in crashes. The most complete example came from a B-17 that crash-landed in the Solomon Islands in August 1942. The aircraft had been damaged by Japanese fighters during a bombing mission against Japanese shipping. With multiple engines failing and the aircraft losing altitude rapidly, the pilot had no choice but to attempt a forced landing on a small island. The crew survived the crash landing and managed to evade capture initially, but in their haste to escape the aircraft before Japanese forces arrived, the bombardier had only partially destroyed the Norden. The thermite grenade had damaged the optical system, but left much of the mechanical computer and stabilizer assembly intact enough for technical examination. Japanese recovery teams transported the captured bombsight to Rabaul, the major Japanese base in the southwest Pacific. From there, it was flown to Japan aboard a transport aircraft in September 1942. Upon arrival in Tokyo, the device was delivered to the Koku Gijutsu Kenkyujo, the Air Technical Research Institute at Tachikawa Airfield. This was the same organization that would later conduct comprehensive examinations of captured B-17 bombers. Commander Minoru Suzuki of the Imperial Japanese Navy's Technical Division headed the initial examination team. Suzuki, an aeronautical engineer with graduate training in precision mechanics, had spent the 1930s studying bombsight development. He understood immediately upon seeing the captured Norden that Japanese technical intelligence had obtained something of extraordinary significance. The examination began with careful disassembly. Each component was photographed before removal. Measurements were recorded, parts were examined under magnification. The stabilizer unit with its 3 gyroscopes received particular attention. Japanese engineers carefully noted the gyroscope mounting system, the gimbal arrangement, and the damping mechanisms that isolated the sight from aircraft vibration. What struck the examination team immediately was the precision of manufacturing. Bearing surfaces were machined to tolerances that Japanese aircraft instrument factories rarely achieved. Gear teeth showed identical spacing and profile across multiple gear trains. The gyroscopes themselves spun with such perfect balance that vibration was essentially undetectable. This was not laboratory-quality prototype construction. This was precision manufacturing implemented at production scale. The optical system, despite damage from the attempted thermite destruction, revealed sophisticated lens grinding and coating techniques. Japanese optical companies like Nippon Kogaku, which produced cameras and military optics, understood lens manufacturing, but the Norden's optical train showed integration of multiple elements, with coatings that reduced light loss and improved image clarity beyond what Japanese military optics typically achieved. The mechanical computer presented the greatest challenge to understanding. This assembly of gears, cams, shafts, and differential mechanisms performed continuous ballistic calculations. As the bombardier tracked the target, the computer constantly updated the release point based on observed ground speed, drift angle, altitude, and preset bomb characteristics. Understanding what each component did required reverse engineering not just the mechanism, but the mathematical principles it embodied. Preparing and narrating this story took us a lot of time, so if you are enjoying it, subscribe to our channel. It means a lot to us. Now back to the story. Lieutenant Commander Takeo Yoshimura, a specialist in fire control systems, led the analysis of the computing mechanism. Yoshimura had worked on Japanese naval bombsights and understood the ballistic equations involved in bomb aiming. His team spent weeks tracing each gear train, determining what input each component received and what output it produced. Slowly, the logic of the Norden's design became clear. The device measured ground speed by tracking target motion through the telescope. The bombardier kept crosshairs aligned on the target while the aircraft flew toward it. The rate at which he had to adjust the sight to maintain alignment revealed the aircraft's actual speed over ground. Simultaneously, any lateral drift caused by crosswinds became apparent as the bombardier compensated to keep the target centered. These measurements fed into the mechanical computer. The computer incorporated preset information about bomb ballistics, altitude, and atmospheric conditions. Using these inputs, plus the real-time measurements of speed and drift, it continuously calculated the point in space where bombs should be released to hit the target. As the aircraft approached this release point, Indicators showed the bombardier how to adjust heading to maintain the proper approach path. At the precise release moment, the sight could trigger the bombs automatically, or the bombardier could release manually based on the sight's indicators. The sophistication of this mechanical calculation exceeded anything in Japanese bomb sights. Japanese horizontal bombing at altitude relied on manual calculation by the bombardier using prepared tables and slide rules. The bombardier would estimate ground speed, factor in observed wind, consult tables for the appropriate lead angle, and manually release bombs when the target appeared at the calculated point in the bomb sight. Accuracy depended heavily on bombardier skill and experience. The Norden automated these calculations and performed them continuously, updating solutions dozens of times per second. A mediocre bombardier using a Norden could achieve accuracy that the best Japanese bombardier using manual methods could not match. More significantly, the Norden's accuracy remained consistent across varying conditions. Wind changes, altitude variations, and speed fluctuations were automatically compensated for by the mechanical computer's continuous recalculation. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. December 1942. Commander Suzuki's team had completed their technical analysis. They prepared a comprehensive report documenting every aspect of the Norden's design, construction, and operating principles. The report included detailed drawings, technical specifications, and assessment of manufacturing requirements. Distribution was carefully controlled. Senior officers in both the Imperial Japanese Army and Navy received copies. Aircraft design bureaus received technical data relevant to their work. Fighter Command received information about American bombing doctrine and tactics. The conclusions reached by Japanese engineers carried profound implications. The Norden represented a level of precision manufacturing that Japanese industry could not readily duplicate. Producing such a device at scale would require machine tool precision, quality control processes, and manufacturing integration that exceeded current Japanese capabilities. But the more disturbing conclusion was what the Norden revealed about American bombing doctrine and the effectiveness of high-altitude strategic bombing. American heavy bombers equipped with Norden bombsights could operate at altitudes where Japanese fighters had difficulty intercepting and where anti-aircraft fire was far less effective. From these altitudes, they could deliver bombs with accuracy sufficient to destroy specific industrial facilities, rather than simply devastating entire urban areas. If American bomber production reached the levels that captured B-17 construction suggested was possible, and if those bombers carried Norden bombsights enabling genuine precision from high altitude, Japan's industrial capacity would become vulnerable to systematic destruction. Japanese fighter pilots had already encountered B-17s over targets in the Pacific. They reported that the American bombers flew in tight formations at altitudes around 25,000 feet or higher. Attacking such formations proved difficult. The bombers' defensive armament created overlapping fields of fire. Fighters attempting stern attacks faced multiple machine guns. Beam attacks exposed the fighter to fire from multiple bombers. Head-on attacks required closing rates that gave pilots only seconds to aim and fire. Even when Japanese fighters successfully engaged the formations, shooting down B-17s proved frustratingly difficult. The bombers were heavily constructed with redundant systems. They could sustain battle damage that would destroy Japanese bombers and still return to base. Multiple engine hits were often required to bring one down, and while all this combat occurred, the B-17s continued toward their targets. Bombardiers hunched over Norden bombsights, tracking aim points through telescopes, allowing mechanical computers to calculate release points. The Imperial Japanese Navy conducted its own bombing operations against Allied targets throughout the Pacific, using twin-engine bombers like the Mitsubishi G3M and G4M. These aircraft typically bombed from altitudes between 10,000 and 15,000 feet, substantially lower than American B-17s. Japanese bombsights were adequate for their doctrine, which emphasized torpedo bombing and dive bombing for precision attacks rather than high-altitude horizontal bombing. The Navy's Type 90 bombsight, developed in the early 1930s, used optical principles similar to earlier American and European designs. The bombardier visually tracked the target and manually calculated release point based on observed ground speed and drift. Skilled bombardiers achieved respectable accuracy under favorable conditions, but results varied significantly based on individual proficiency and environmental factors. The Army Air Force used similar bomb sights in their heavy bombers. The Mitsubishi Ki-21 and later Ki-67 bombers carried sights that required manual calculation and timing. Japanese doctrine did not emphasize high-altitude precision bombing, partly because Japanese bombers lacked the performance to operate effectively above 20,000 feet, and partly because existing bomb sights could not deliver adequate accuracy from such altitudes, even if the aircraft could reach them. Examining the Norden forced Japanese planners to confront an uncomfortable reality. American bombing doctrine was built around capabilities that Japanese forces could not match. The combination of high-altitude heavy bombers and precision bomb sights represented a systematic approach to strategic warfare that would place Japanese industrial facilities at grave risk once American production delivered sufficient numbers of aircraft to the Pacific theater. In January 1943, the Japanese Army Air Force authorized a program to develop an improved bomb sight, incorporating some principles learned from examining the captured Norden. The project, assigned to Tachikawa Aircraft Company's technical division, aimed to create a gyro-stabilized sight with mechanical computing capability. Engineers understood the principles involved. The challenge was manufacturing components to the required precision and integrating them into a reliable system that could be produced in meaningful quantities. Development proceeded slowly. Creating precision gyroscopes required specialized manufacturing equipment and expertise that was concentrated in a few Japanese facilities. Machine tools capable of cutting gears to the necessary tolerances were scarce. Quality control processes adequate for aircraft structural components proved insufficient for instrument-grade precision parts. Engineers could build prototype bomb sights that demonstrated the principles, but transitioning to production revealed the same fundamental limitations that examination of the B-17 had exposed regarding American mass production capabilities. By mid-1943, Japanese engineers had produced approximately a dozen prototype, advanced bomb sights. Testing revealed mechanical reliability problems. Gyroscopes failed prematurely. Gear trains developed excessive backlash. Optical elements degraded under operational vibration and temperature cycling. The prototypes worked adequately under laboratory conditions, but failed to meet the reliability standards required for combat operations. Even if these technical problems had been solved, production capacity remained a fundamental constraint. Manufacturing one advanced bomb sight required hundreds of hours of skilled machinist time. Scaling to produce thousands of units would require diverting manufacturing capacity and skilled workers from other critical programs. Japanese industrial planners faced constant allocation decisions, choosing which weapons systems received priority for limited resources. Meanwhile, American B-17 production continued accelerating. Intelligence reports reaching Tokyo documented expanding American bomber strength in England and the gradual build-up of air forces in the Pacific. Each bomber presumably carried a Norden bombsight. Each bombardier had received months of training. The systematic application of precision bombing was becoming operational reality in Europe and would inevitably extend to the Pacific. The first major test of American high-altitude precision bombing doctrine against Japanese targets came in April 1942, when 16 B-25 medium bombers launched from the aircraft carrier USS Hornet attacked Tokyo and other Japanese cities in what became known as the Doolittle Raid. These aircraft bombed from low altitude and achieved minimal accuracy, but the psychological impact of the attack on Japanese leadership was profound. American bombers had struck the homeland. The raid prompted urgent Japanese efforts to expand fighter defenses and develop better methods for intercepting high-altitude bombers. Fighter units received priority for the newest aircraft. Anti-aircraft artillery deployments increased around critical industrial facilities. Early warning systems expanded. But these defensive measures addressed the symptoms rather than the underlying strategic vulnerability. Japanese war production depended on a relatively small number of critical industrial facilities. The Nakajima aircraft engine plants at Musashino near Tokyo produced a substantial percentage of Japanese aircraft engines. Mitsubishi's Nagoya facilities manufactured airframes and engines. Steel production concentrated in a few major mills. Oil refineries processing petroleum from the Dutch East Indies were few and vulnerable. If American bombers with Norden bombsights could attack these facilities with the accuracy demonstrated in testing, Japanese war production would face systematic degradation that could not be easily countered. The strategic situation deteriorated through 1943 and into 1944. American forces advanced through the Pacific, capturing islands that brought Japan within range of heavy bomber operations. The development of the B-29 superfortress provided the United States with a bomber specifically designed for long-range strategic bombing missions against Japan. This aircraft incorporated pressurization, remote-controlled defensive armament, and performance-enabling operations at altitudes exceeding 30,000 feet. Commander Suzuki, who had led the initial examination of the captured Norden bombsight, continued following American bombing operations in Europe through intelligence reports. The results provided sobering confirmation of what the technical analysis had predicted. American bomber formations attacked German industrial targets with increasing effectiveness. While accuracy never matched the optimistic pre-war test range results, it proved sufficient to systematically destroy critical facilities. Reports from Europe documented attacks that placed substantial percentages of bombs within target areas measured in hundreds of yards rather than miles. Ball-bearing plants at Schweinfurt suffered severe damage. Aircraft factories across Germany absorbed repeated attacks. Synthetic fuel plants, critical to German war production, given their lack of natural petroleum resources, faced sustained bombing campaigns that progressively reduced output. German defensive responses paralleled Japanese efforts. Fighter strength increased. Anti-aircraft artillery deployments expanded dramatically. Tactics evolved to counter American bomber formations. Yet despite these measures, and despite inflicting substantial losses on attacking bomber forces, German defenses could not prevent the systematic destruction of critical industrial capacity. The lessons from Europe were clear to Japanese planners who studied the campaigns carefully. High-altitude precision bombing worked, not with the surgical accuracy that pre-war doctrine had envisioned, but with sufficient precision to destroy specific industrial facilities given enough attacks. The Norden bombsight enabled accuracy adequate for strategic effect. American industrial capacity could sustain bomber production and crew training despite losses. Japanese defensive resources were substantially less than what Germany had deployed. Yet German defenses had ultimately failed to prevent catastrophic damage to war production. In November 1944, the strategic bombing campaign against Japan began in earnest when B-29s flying from bases in the Mariana Islands attacked Tokyo. The first raid targeted the Nakajima aircraft engine plant at Musashino. Weather conditions compromised accuracy, and results were disappointing, but the attack demonstrated that Japanese industry was now vulnerable to the same systematic destruction that German industry was experiencing. Each B-29 carried the latest version of the Norden bombsight, the Mark 15 Mod 5, incorporating improvements developed through combat experience in Europe. Bombardiers had trained extensively. Aircraft flew in formation at altitudes where Japanese fighters struggled to intercept effectively. The bombing campaign that Japanese engineers had predicted based on examining the captured Norden 2 years earlier was now operational reality. Initial raids achieved mixed results. High winds at altitude, particularly the jet stream that meteorologists were only beginning to understand, pushed bombs off target. Cloud cover obscured aim points. Japanese fighter defenses, while unable to stop the raids, inflicted losses that concerned American planners. But the campaign continued with increasing intensity and improving accuracy as crews gained experience. The systematic examination of the captured Norden bombsight had provided Japanese engineers with detailed understanding of American bombing capabilities 2 years before those capabilities were fully employed against Japanese targets. This advanced knowledge, however, proved insufficient to develop effective countermeasures. Understanding what the enemy could do was not equivalent to preventing them from doing it. Japanese fighter production, which had received highest priority for resources, continued through 1944 despite increasing difficulties. The Nakajima Ki 84 Frank fighter entered production as an attempt to create an aircraft capable of intercepting B-29s effectively at high altitude. The Kawasaki Ki 100, a stopgap design using existing airframe tooling with a different engine, proved to be an excellent fighter, but arrived too late and in too few numbers to significantly impact the strategic situation. More fundamentally, Japanese pilot training had collapsed under the cumulative attrition of 3 years of intensive warfare. Experienced pilots had been killed in combat faster than training programs could replace them. Fuel shortages forced reductions in training hours for new pilots. By late 1944, Japanese fighter pilots reaching operational units often had less than 100 hours total flying time, inadequate preparation for engaging American bomber formations. The bombing campaign evolved through the winter of 1944 to 1945. Major General Curtis LeMay, who assumed command of B-29 operations in January 1945, made a controversial decision to shift tactics. High-altitude precision bombing had achieved limited success against Japanese industrial targets. LeMay ordered a transition to low-altitude nighttime incendiary attacks against Japanese cities. This tactical shift reflected several realities. Japanese urban areas, with their dense concentrations of wooden structures and cottage industry, were vulnerable to fire. Night operations reduced fighter and anti-aircraft effectiveness. Low-altitude attacks improved bombing accuracy and reduced the navigational and weather challenges that had complicated high-altitude operations. The Norden Bombsight, designed for precision daylight bombing, became less relevant to area incendiary attacks. The first major incendiary raid struck Tokyo on the night of March 9 to 10, 1945. Over 300 B-29s dropped incendiaries from altitudes between 5,000 and 9,000 feet. Fires spread rapidly through densely packed neighborhoods. The attack killed an estimated 100,000 people and destroyed approximately 16 square miles of the city. Subsequent raids struck Nagoya, Osaka, Kobe, and other major urban centers. The shift to incendiary attacks represented a departure from the precision bombing doctrine that the Norden Bombsight had been designed to enable. American planners had concluded that the combination of Japanese urban geography, defensive challenges, and operational realities made area attacks more effective than continued attempts at precision bombing of specific industrial facilities. The decision was controversial then and remained debated by historians, but its immediate effectiveness was undeniable. Japanese war production, already strained by years of war and increasing shortages of raw materials, collapsed under the combined effects of the bombing campaign, naval blockade, and the systematic destruction of the transportation infrastructure. Aircraft production, which had peaked at over 28,000 airframes in 1944, fell dramatically through the first half of 1945. By July, monthly production had declined to barely 1,000 aircraft. The Nakajima Musashino plant, which Japanese engineers had identified in 1943 as critically vulnerable to precision bombing, sustained repeated attacks. The facility never completely ceased production, but output declined drastically. Mitsubishi's Nagoya facilities suffered similar sustained damage. Even facilities that remained physically intact often could not operate effectively due to disrupted supply chains, lack of raw materials, and the breakdown of transportation systems. Commander Suzuki, whose examination of the captured Norden Bombsight in late 1942 had led to prescient warnings about Japanese vulnerability to strategic bombing, survived the war. In interviews conducted during the occupation period, he reflected on what Japanese intelligence had learned from studying American equipment and what that knowledge had meant for Japanese defense planning. The Norden Bombsight examination had provided accurate understanding of American bombing capabilities years before those capabilities were fully employed. Japanese planners had known what was coming. They had attempted to develop countermeasures. They had expanded fighter defenses and anti-aircraft artillery. They had worked to develop improved bomb sights and better high-altitude fighters. None of these measures proved adequate to prevent the systematic destruction of Japanese war production. Suzuki's post-war assessment was sobering. The captured Norden had revealed not just a piece of technology, but an entire strategic approach to warfare. The bomb sight represented American confidence in mechanical precision, systematic methodology, and the application of industrial mass production to military problems. These were not simply technical advantages but reflected fundamental differences in how American and Japanese societies organized industrial production. The Norden required precision manufacturing at scale. Producing 14,000 units during the war meant creating production infrastructure, training workers, implementing quality control, and managing supply chains for thousands of precision components. This mirrored the broader pattern visible in the captured B-17 bombers that Japanese engineers had also examined. American industry could produce complex equipment to precise tolerances in quantities that Japanese industry could not match. Understanding this disparity in 1942 had not enabled Japanese industry to overcome it. The gap was not primarily technical knowledge but industrial organization, machine tool capacity, manufacturing infrastructure, and the systematic application of precision production methods across entire industrial sectors. These capabilities could not be quickly developed or easily replicated. After Japan's surrender in August 1945, American technical intelligence teams arrived in Japan to assess Japanese military technology and industrial capacity. The examination became reciprocal as American engineers toured Japanese aircraft factories, examined Japanese equipment, and interviewed Japanese engineers and military personnel. American teams discovered that Japanese engineers possessed sophisticated understanding of American equipment, including the Norden Bombsight. Captured examples had been thoroughly studied. Technical principles were well understood. The challenge had never been understanding what Americans had achieved, but rather implementing similar capabilities within Japanese industrial constraints. The captured Norden bomb sites that Japanese engineers had examined were eventually turned over to American occupation authorities. The devices, damaged by years of study and disassembly, were no longer functional, but they had served their purpose. They had taught Japanese engineers what they faced and revealed the scale of the challenge confronting Japanese defenses. In the decades following the war, the Norden bombsight became something of a historical controversy. Critics pointed out that combat accuracy never approached the precision achieved on test ranges. Circular errors of several hundred feet were typical, rather than the 200-foot accuracy claimed in pre-war testing. Weather, combat stress, defensive fire, and operational realities all degraded performance below theoretical capabilities. Some historians argued that the Norden represented overinvestment in a technology that never delivered on its promises, that the resources devoted to developing and producing the device would have been better spent elsewhere, that simpler bomb sights would have achieved comparable results at far lower cost. These arguments have merit when examining the specific accuracy statistics from combat operations. But this analysis misses the strategic significance that Japanese engineers grasped when examining captured examples in 1942. The Norden enabled high-altitude bombing with sufficient accuracy for strategic effect. Not surgical precision, but accuracy adequate to systematically destroy industrial facilities given sustained campaigns. This capability, combined with American bomber production and crew training capacity, created a strategic threat that Japanese defenses could not effectively counter. The examination of captured American equipment provided Japanese intelligence with accurate understanding of American capabilities. The captured B-17 revealed American mass production methods. The captured Norden bombsight revealed American bombing doctrine and the technical basis for high-altitude precision attacks. Together, these examinations painted a comprehensive picture of the strategic bombing campaign that would ultimately contribute to Japan's defeat. Japanese engineers who conducted these examinations in 1942 and 1943 reached conclusions that proved accurate. They understood that American industrial capacity exceeded Japanese capacity by margins too large to overcome through determination or tactical innovation alone. They recognized that systematic strategic bombing would degrade Japanese war production progressively, and that defensive measures would prove inadequate to prevent this outcome. This knowledge did not translate into effective countermeasures because the disparity was too fundamental. The gap was not a specific technology that could be copied or a particular tactic that could be countered. The gap was comprehensive industrial capacity, the ability to produce precision equipment at scale, to train personnel systematically, to sustain operations despite losses, and to apply overwhelming material resources to achieve military objectives. The story of Japanese engineers examining the captured Norden Bombsight illustrates both the value and the limitations of technical intelligence. Understanding an opponent's capabilities is essential for effective defense planning. The examination provided accurate intelligence that informed Japanese defensive preparations, but understanding what the enemy could do was not equivalent to developing the means to prevent them from doing it. The Norden Bombsight dropped from operational use quickly after World War II ended. Advances in radar bombing and eventually precision-guided munitions made the complex mechanical sight obsolete. Modern warfare moved beyond the paradigm that the Norden represented, where human bombardiers guided bombs toward targets using optical sights and mechanical computers. But during World War II, the Norden embodied the state-of-the-art in bombing technology. It represented American confidence that precision bombing could achieve strategic objectives. It enabled operations at altitudes where defensive fire was less effective. It provided the technical foundation for the systematic bombing campaigns that destroyed German and Japanese war production. Japanese engineers who examined captured examples understood immediately that they were seeing not just a sophisticated instrument, but evidence of an entire approach to warfare that their nation was not equipped to counter effectively. The precision of the manufacturing, the sophistication of the mechanical computing, the integration of gyroscopic stabilization and optical tracking, all demonstrated industrial and technical capabilities beyond what Japanese industry had achieved. Up next, you've got two more standout stories right on your screen. If this one hit the mark, you won't want to pass these up. Just click and check them out. And don't forget to subscribe and turn on the notification bell so you don't miss any upload from us.